Hey everyone, and welcome to another deep dive. Today we'll be tackling something truly mind-bending.
Oh, sounds exciting.
It is, I promise. We're going to be looking at the superposition principle in quantum mechanics.
Quantum mechanics, always a fascinating topic.
Right. We're going to unpack how something can be in multiple states at the same time.
Multiple states at the same time, that's wild.
It is, and that's not all. We'll also explore what that means for our understanding of reality and how this principle is driving the development of incredible new technologies.
Sounds like we have a lot to cover. Where are we starting?
Our guide for this deep dive is an essay by Jorgo Schneppat called Superpositionsprinzip, Basis der Quantenmechanik erklärt.
Okay, so for our English-speaking listeners, that translates to superposition principle, the basis of quantum mechanics explained.
Exactly.
I've read Schneppat's work before. He really gets to the heart of why this principle is so fundamental to quantum mechanics.
You're right. And while quantum mechanics can sometimes feel intimidating, I promise we'll break it down into digestible pieces.
I'm sure you will. You always do.
Thanks. So to set the stage, what exactly is superposition?
Okay, so superposition is the idea that quantum objects, like electrons, can exist in multiple states at the same time.
So it's not just that we don't know what state they're in.
Exactly. It's not a lack of information on our part. They genuinely inhabit all those states simultaneously, at least until we measure them.
Okay, so it's a fundamental property of the quantum world, not just an observational limitation.
Or precisely.
Do you have an example to help visualize this?
Well, you can think of it a bit like a spinning coin being both heads and tails until the moment it lands.
Oh, I see. It's in this kind of in-between state.
Yes. And Schneppat actually uses the German term Überlagerungszustand to describe this, which kind of translates to a layered state, if you will.
A layered state of being in multiple states at once. That really does challenge how we usually think about reality.
I agree. We tend to assume things have one definite state.
Right, like a chair is a chair, a table is a table. Those things don't exist in multiple states at once.
Exactly, and that's where quantum mechanics throws a wrench into our classical understanding. Jorgo Schneppat really drives this point home in his essay.
So how do we even begin to wrap our heads around this idea of multiple states existing at once? Is there a way to visualize it or connect it to something tangible?
Well, a classic example that Schneppat highlights is the double slit experiment. It's almost like a rite of passage for anyone trying to understand superposition.
Okay, tell me more about this double slit experiment.
So imagine firing electrons at a barrier with two slits.
Okay, I'm picturing it.
Now, if electrons behave like tiny marbles, we'd expect them to go through one slit or the other, forming two distinct bands on a screen behind the barrier.
Makes sense. It would be kind of like spraying paint through stencils, right?
Exactly.
Yeah.
But that's not what happens. Instead, we see an interference pattern on the screen with alternating bright and dark bands.
Wait, so the electrons are doing something else entirely?
Yes. It's as if each electron went through both slits simultaneously and interfered with itself like a wave.
So a single electron is somehow in two places at once.
That's the thing. It is. And it only makes sense if we accept that the electron exists in a superposition of states, meaning it's in a state of going through both slits simultaneously until it hits the screen.
This is where my brain starts to hurt a little.
I know, it's a lot to take in. Schneppat really emphasizes how the double slit experiment forces us to abandon our classical intuition and embrace the strangeness of quantum behavior.
So we can actually see this superposition in action through this interference pattern.
You could say that. It's like the electron's fingerprint, revealing its superposition nature.
That's one way to put it. That makes it a little easier to grasp.
I'm glad.
Now, you mentioned that scientists use things like wave functions and the Schrödinger equation to describe these multiple states.
I did.
Could you give us a simple explanation of what those are without getting too technical?
Of course. Think of the wave function as a map of possibilities for a quantum object. It describes the probability of finding the object in a particular state when we measure it.
So it's not like a fixed location, but more like a range of potential locations.
That's a good way to think about it, yes.
And what about the Schrödinger equation?
Well, that's like the instruction manual for this map, telling us how the probabilities change over time.
Okay, so we're not dealing with certainties here, but rather probability.
Exactly. It's a probabilistic view of reality, which is a major departure from classical physics, where we like to think in terms of definite states and predictable outcomes.
This is definitely stretching my brain. So we've got this electron in its superposition state, interfering with itself like a wave. But I have a feeling things get even weirder when we start talking about multiple particles, right?
You'd be right about that.
And I know Schneepat had some fascinating things to say about this, especially the idea of superposition.
He did, and that's exactly where we're headed next.
Awesome. I'm ready for more.
Great. Then let's dive into the world of quantum entanglement. So we've seen how superposition plays out with individual particles, right?
Yeah, like with that electron in the double slit experiment.
Right. And even with entangled pairs. But where it really gets interesting, I think, at least from a practical standpoint,
Okay, where's that?
is in how it's being harnessed to build quantum computers.
Ah, quantum computers. Everyone's talking about how they're going to revolutionize everything.
It seems that way.
But to be honest, I'm still not entirely sure I understand how they work.
I understand.
What makes them so different from the computers we use every day?
Well, the key difference is really how they process information.
Okay, how so?
Our everyday computers use bits.
Right, which can be either a 0 or a 1.
Exactly. Quantum computers, though, use qubits.
Qubits, okay. What's the difference?
The difference is that they can be in a superposition of both 0 and 1 at the same time.
It's like that spinning coin again, right?
Exactly,
Yep.
existing in both states until it's measured.
So instead of just having those two options, 0 or 1, a qubit can explore a whole range of possibilities simultaneously.
Yes, precisely.
That sounds really powerful.
It is.
But I'm not sure I get how that translates into actual computing.
Well, think of it this way. A single qubit can perform multiple calculations at once
Because...
because it's exploring all those possibilities simultaneously.
Oh, I see.
This is what's called quantum parallelism.
Quantum parallelism. Okay.
Now imagine a system with multiple qubits all entangled with each other. You suddenly have a machine that can perform a massive number of calculations in parallel, exponentially more than a classical computer.
Wow, that's incredible.
It is. That's why there's so much excitement about quantum computers and their potential.
So it's not just that they're faster.
Right. It's not just about speed.
It's that they operate in a completely different way.
Yeah.
Leveraging superposition to tackle problems in a way that classical computers just can't.
Exactly. And Schneepat actually does a great job of illustrating this in his essay.
Oh, how so?
Well, he gives some specific examples, like Grover's search algorithm, for
What
words.
was that?
Well, it can search through unsorted data much faster than any classical algorithm. And then there's Shor's algorithm.
What does that one do?
Shor's algorithm has the potential to break the encryption we currently use for online security.
Okay, so that's both fascinating and a bit unsettling.
It is, a little bit. It's like we're unlocking this whole new level of computing power, but there are potential risks that come along with it.
It's like every powerful technology, I guess, a double-edged sword.
Yeah, that's a good way to put it. But, focusing on the positive, Schneepat also talks about how quantum computing could lead to breakthroughs in lots of different fields.
Oh, like what?
Well, like medicine, materials science, and our understanding of the universe.
Yeah, I can see how it could be useful in those areas.
For example, quantum computers could help us simulate complex molecules to design new drugs, maybe, or materials with specific properties.
Okay, so we're just scratching the surface of what might be possible.
That's right.
But I do have a question.
Sure. What is it?
If superposition is so fragile, like we talked about earlier, how do we keep these qubits in their superposed states long enough to actually do any meaningful calculations?
Ah, yes, that's the million-dollar question right now in quantum computing.
Really?
Yeah.
So what's the problem?
Decoherence. That tendency for superposition to collapse due to interactions with the environment, you see.
Oh, right. We talked about that.
It's a huge challenge. Like, imagine you're trying to balance a pencil on its tip.
Right.
The slightest disturbance can cause it to topple over.
So how do you stop that from happening?
Well, researchers are exploring a bunch of different approaches.
Well, Jess.
One is to isolate the qubits as much as possible, try to minimize any interactions with the surrounding environment.
How do they do that?
Well, one way is by cooling them down to near absolute zero.
Wow, that's cold.
It is. And then another approach is to develop error correction techniques,
Okay, what would those do?
Well, they can detect and correct errors caused by decoherence.
So it's a race against decoherence.
That's a good way to think about it, yeah. Trying to outsmart it with some clever engineering and algorithms.
And how are they doing so far?
The progress is actually pretty remarkable. Just a few years ago, keeping a qubit in superposition for more than a few nanoseconds was a major accomplishment.
Really? Just a few nanoseconds?
Yeah. But now we're talking about coherence times on the order of minutes.
Minutes. Wow, that's a huge jump.
It is. And it opens up a whole new world of possibilities.
That's incredibly encouraging. It sounds like quantum computing is moving from, like, science fiction into something tangible.
It really is.
But I'm curious, Schnepp had also mentioned other applications of superposition, right?
He did, yes.
Not just computing.
Right. He talked about things like secure communication and even ultra-precise measurements.
Oh, yeah, I remember that. Okay, let's start with quantum communication then. How does that work?
Well, remember how we talked about entangled particles?
Yeah, how they're linked even across vast distances.
Exactly. Well, scientists are actually using this property to develop ultra-secure communication networks.
Okay, tell me more about that.
Well, the idea is to use those entangled particles to create keys,
Keys for what?
encrypting and decrypting messages.
Oh, interesting. So it's like having a secret code that's impossible to crack.
Exactly. Because any attempt to intercept the key would disturb the entanglement, you see.
And what would that do?
It would alert both parties to the intrusion.
So it's like having an unbreakable seal on your messages.
Yes, that's a good way to think about it.
Wow. That is incredible. It's like something out of a spy movie.
It is pretty cool, and because it relies on those fundamental laws of quantum mechanics, it offers a level of security that's just impossible to achieve with classical methods.
So it's totally unhackable.
Pretty much, yeah.
That's amazing. And what about those ultra-precise measurements Schnepp mentioned? What role does superposition play there?
Okay, so this is where we get into the realm of quantum metrology.
Quantum metrology, okay.
It's all about using quantum phenomena like superposition to make incredibly precise measurements.
Measurements of what?
Well, things like time, gravity, magnetic fields, even temperature.
Okay, that sounds pretty technical. Can you give me an example of how it works, like in practice?
Sure. Think of atomic clocks.
Oh, yeah, those are super accurate.
They are. They're the most accurate timekeeping devices we have. And they rely on the superposition of energy levels within atoms.
How so?
Well, by precisely measuring the transitions between those energy levels, we can keep time with incredible accuracy.
So we're talking about clocks that are so precise they lose less than a second over billions of years.
Yeah, pretty much.
That's mind-boggling.
It is. But the applications actually go beyond just keeping time. Quantum metrology is being used to develop these ultra-sensitive sensors for all sorts of things.
What kinds of things?
Well, things like medical imaging, navigation, mineral exploration, even environmental monitoring.
Wow, so superposition isn't just about weird quantum effects.
No, not at all.
It's actually having a real-world impact on the world around us.
Absolutely. And we're really just at the beginning, you know.
Oh, how so?
As we continue to explore the strange and beautiful world of superposition, who knows what other amazing applications we'll discover.
It really does feel like we're on the verge of a whole new technological era, powered by the principles of quantum mechanics.
I agree.
But before we get too ahead of ourselves, I think it's important to step back for a moment and reflect on what we've learned so far about superposition.
That's a good idea.
It's truly a concept that challenges our fundamental understanding of reality, right?
It is.
It reveals this universe where particles exist in this haze of possibilities until the moment of measurement.
Exactly. And as Schnepp so eloquently argues in his essay, embracing this new understanding requires us to let go of our classical intuitions and embrace the inherent uncertainty and strangeness of the quantum world.
That's a powerful thought. It seems like the more we learn about the quantum world, the more we realize how much we don't know.
That's very true.
It is a bit humbling, I have to admit. But, you know, it's also really exciting.
Oh, absolutely.
And on that note, I think it's time to start wrapping up our deep dive on the superposition principle.
Sounds good.
But before we go, I want to circle back to Yorgo Schneppat's essay for a moment. It's really been such a valuable guide for us.
It really has. Schneppat's insights are always thought-provoking.
You know, one thing that really struck me was how he doesn't just explain the science, but also delves into the philosophical side of things.
Oh, absolutely. He really challenges us to think about what this principle means for our understanding of reality itself.
Like, if particles can be in multiple states at once, does that mean there are multiple versions of us existing in parallel universes?
Yeah. It's a mind-blowing concept, isn't it? It really challenges our everyday perception of a singular, linear reality.
Really does. I mean, that's not how we experience the world, right?
Yeah. No, not at all. But Schnepp argues that quantum mechanics forces us to confront the limitations of our classical worldview. The one that assumes a clear distinction between the observer and the observed, cause and effect, all those things we take for granted.
Right, but in the quantum realm,
In the quantum realm, all those lines start to blur.
it's almost like we're not just passive observers of the universe, but active participants in how it unfolds.
Exactly. And that raises some fascinating questions about the role of consciousness. Some physicists even speculate that consciousness itself might be a quantum phenomenon.
Whoa, really? So our consciousness could be what causes the collapse of superposition.
It's an idea that some people are exploring, for sure.
That's pretty wild. It feels like with every answer we uncover in quantum mechanics, it just leads to even more profound questions.
It really does. But I think that's also the beauty of it all. It's this endless quest for understanding. And as Schneppet reminds us, the quantum revolution is still in its early stages.
Oh, for sure. We're just beginning to grasp the implications of these concepts.
Exactly, like superposition.
And who knows what other mysteries and wonders are out there waiting to be discovered as we continue to explore the quantum realm.
I'm excited to find out.
Me too. So, as we wrap up this deep dive on superposition, what are some key takeaways you'd like to leave our listeners with today?
Well, first and foremost, I would say embrace the strangeness. Don't be intimidated by the counterintuitive nature of quantum mechanics. Instead, allow yourself to be captivated by its elegance and beauty.
I love that. Any other words of wisdom?
Oh, and never stop questioning and exploring. There are so many resources available to learn about quantum mechanics, from books and articles to online courses and videos. And don't be afraid to reach out to experts, engage in discussions. The more perspectives we gather, the richer our understanding becomes.
That's such great advice. And remember, even the experts are still grappling with the profound implications of superposition. It's a journey of discovery that we're all on together. So to everyone listening, keep those minds curious and keep exploring the mind-bending world of quantum mechanics. Who knows what incredible breakthroughs and insights await us in the years to come. Until next time, keep diving deep.